All right, guys, so here we are again. Now let's take a look at the derivative exploration. I'm just making sure I'm not looking at the wrong version here. No, that's good. That's good. I was like, I saw red writing here. I was like, did I get the teacher's version? Okay, so this is basically just an exercise to help you explore the meaning of derivatives. So for the function 3x plus 7, what is the change in the output each time the input increases by 1? So remember 3x plus 7, 1, 2, 3, 4, 5, 6, 7. And then 3x slope. I'm not going to draw this perfectly to scale, okay? Not to scale. In other words, I'm not vetting that that's coming down exactly to scale on where the tick marks are there. None of that matters, though. This is a 3x plus 7 plot, or sketch, I should say, not a plot. And what is the change in each output each time increases by 1? Well, each time we increase by 1, we go up 3, right? And each time we increase 1, we go up 3 again, up to there, and so on. Each one of these is a chain. We go 1 unit to the right, we go 3 units up. And so therefore, the answer to this one would be 3. And each time, for the function negative 2x plus 5, what is the change in output each time the input increases by 1? Well, it's going to be the same thing there. A negative 2x plus 5, we'll just put 5 here, and negative 2x will be a little bit steeper than a 1x. And then, of course, decreasing. And each time we go 1 unit to the right, we've dropped 2 units. Okay, this way you'd want to write it. Actually, if you want to write it properly, you'd go like this. 1 unit to the right, 2 units down. 1, 2. 1 unit to the right, 2 units down. 1 unit to the right, 2 units down, and so on. And so for number 2, it would simply be 2. And so these are Algebra 2 based questions, and they're trying to jump from the Algebra 2 based questions into giving you a little time to reflect upon what you've learned now in these most recent chapters. And then number 3, in a linear function, the change in the output each time the input increases by 1 can be approximated by what? So in both of these cases, when we increase by 1, what represents that? Well, 3x plus 7, negative 2x plus 5, both of these are in what we learned as slope-intercept form, mx plus b. The 3 is this 3, the negative 2, what did they say for 2? Do I need to put negative or positive? Let me reread it. What is the change in the output each time? It would be negative. Well, the change would just be 2. So you could just put positive 2 there because they're just asking for the change. But 3, the answer to that is that negative 2 and 3 are the slope. Okay? And in this case, they use the word approximated, but in this case, the approximation is exact. This is actually an exact calculation, not an approximation. And the slope is what yields that exact value. And so I think we're pretty good there. Again, if you put negative 2 here, that's fine. Technically, the way it's worded is what is the change, and the change doesn't necessarily imply a direction. It decreases by 2, or it has a change of 2 units. I could, like if I wrote it has a change of 2 units, I don't need to say whether it went down or went up. And I don't need to say whether it went down or it went up here because they only asked for the change. And the change is just 2 units of change, 3 units of change. If they asked separately, is it increasing or decreasing, you would say this is increasing by 3 units or this is decreasing by 2 units. But when you just ask for change, change doesn't necessarily imply a sign. So I didn't write this original. I've edited it a lot, but I can't catch every error. So strictly speaking, change doesn't have any directionality to it. It can be change in either direction. Therefore, you could say it has 2 units of change, and you could get away with writing a positive. Or because change is ambiguous, you can also interpret change to mean it's not that it doesn't have directionality. It's that it's ambiguous. It can mean non-directional change, or it can mean directional change. So point being is if you put negative 2 or if you put 2, either's actually correct because they use the term change and they didn't use decrease. Like if they said, what does it decrease by each time the output? Actually, if they said, what does it decrease by, then you would say 2 because decrease already implies the negative, So I don't know. I can see it either way. I won't harp on that any longer. I would have worded it a little differently if I had written it originally, but you get the idea. Don't overthink it. So either way is fine, okay? If you thought of it as directional change, you could put negative 2. If you thought of it as just, what's the unit amount of change that happens for each one step, regardless of which direction you go, like absolute value of change, which it can, because it's ambiguous mean, then positive 2 would have been fine. The 3 we already answered, which is the slope. And so now they're trying to segue into some more calculusly based questions and thinking. So they say, okay, and what about a 1 unit increase for 4x? Well, 4a should be pretty routine. 4a is going to be the same as the ones we just did. It will be 4. Now 4b, we've talked about before. This is the y equals 7 function, and they're saying, a 1 unit increase in the input results in what change in the output? And the answer is nothing, because 1, 2, 3, 4, that's totally not to scale. Oh, and I didn't even write it on 4. Sorry about that. 1, 2, 3, 4, right? 1, 2, 3, 4, there we go. Tried to fix the dots there a little bit. There's no change. You're always at a height of 7. You're going to be at a height of 7 over here when you go 1 unit. You're going to be height of 7 here, and then height of 7 there when you go 1 unit. And everywhere you go, you have no change, because that's the definition of a horizontal line, is that it has no slope. There is no change. It is one and the same with the y-intercept. A horizontal line is y equals 0x plus b, and the 0x just drops out, and your b is equal to 7, and 7 everywhere, not just on the y-intercept. It's a special case where the b becomes the y-intercept and every output on the whole domain of the function. And so the answer to 4b is 0. There is 0 change. Okay? And now the answer to C, 4c, is a little different. Okay? So we know now, all right, here's x squared, right? Okay, when x is greater than 0. And let's just take the point 2. Okay? All right, we now know how to do the derivative of this. So the derivative of x squared is equal to 2x. And let's just talk about, like, here's 1, here's 2. And at the point 2 on regular old x squared, we know we get 4. And the derivative of 2 is equal to 4, meaning that right here, at that point, this line has a slope of 4. But that's not, and this is all fine and dandy, and we've learned how to do this now, but they're not quite asking just about that. What they're saying is, well, when I go to 3, how much does this go up by? How much did the actual function increase when I go to 3? And it's not going to be exactly, it's not the same as the linear one. The linear ones, the change is the slope. Like the derivative of 3x is 3. The derivative of negative 2x is 2. The derivative of 4x is 4. But the derivative here is a function itself. And so it won't exactly be 2x. It won't exactly, like here it's the derivative. Here it's the derivative. Here it's the derivative, which we know what that means now. But here it's not exactly the derivative, because they're asking about what the change on actual f of x would be. So if we follow it up, we'll see, and you guys have seen enough of these graphs to know that when I actually draw this to scale, it's more like this. Like these lines are almost overlapped. So this 2x line, which is the slopes of this line, turns out to, when you make the tangent at 2, it turns out that if you only go 1 unit up, this value here on y prime will be really close to the value on y. And so y prime of 2 will be approximately equal to y of 2 when your x values are close to the point of tangency. Okay, so when your x values are close to the point of tangency, they're going to be roughly the same. So our answer to 4c is that, let me see how I want to word this. The answer to 4c, I guess the best way to say it is that, this one I arbitrarily did at 2. I could arbitrarily do one at 5. I could arbitrarily do one at 6. I could do the negative branch, do one at negative 10. And the same principle would apply, where the tangent at any of those points that I labeled will be a good approximation for any of those points. So the first part is it depends on the point, because obviously 100 times 2 is going to be way bigger than 2 times 2. So it depends on the point, x equals a, but once picked, So once you pick that point x equals a, it will be approximated by regardless of where you pick it, once you pick it, it will be approximated by 2x. It will not be equal to 2x, okay? If they're concave up, the tangents are going to be underestimates. If they're concave down, the tangents will be overestimates. So over when concave down, and under when concave up. And you can just see that intuitively. But when the tangent lines, when you're very, very close to the value, it will be nearly identical, okay? So let's say that we didn't do one unit of change, but I just did y prime of 2.01. That will be nearly identical to y of, that's, I mean, it might even, I mean, I'm not going to say it's equal, but it will be nearly identical to y of 2.01. So that gets us through 4C. Now, I don't want to do the whole sheet for you here, okay? I want to just step you through it and see what we're doing here. So here we have the original, here we have x, and then we have 4x. So when we have an x value of 2, 4 times 2 is 8, an x value of 3, 4 times 3 is 12. So this is just a horizontal t-chart, and it's showing you that on linear functions, the increase is always constant. It's 4, it's 4, it's 4, and so on. Okay, here for B, it's telling you what is the pattern that you see. For every time the input increases by 1, what are the differences between the outputs constant? Why or why not? Are there any constant changes? So I'm going to do the first one with you, and then I want you guys to do x cubed on your own. So if we do, and I'll do a vertical chart. So if we have x squared, and then we have our x values, and we have our x squared values, we're going to have, and they want us to use 7, 8, 9, and 10, which is perfectly fine, 49, 64, 81, 100. The difference here is going to be 15. The difference here is not going to be 15. This is going to be 11, and then 6 is at 17. Let's see, 7 would be 71. Yeah, 17. The difference here is going to be 19. Okay, so the first answer is, are the differences between the outputs constant? And the answer is no. Okay, they're clearly not constant. And you can probably predict, look, 15, 17, 19, 11, 1, 21, 21. Check that out. Okay, but look at what happens. Although the differences in the outputs aren't constant, since it's squared, the differences of the differences are. And that's because if I do two derivatives, so first derivative of x squared would be 2x, and so those differences are going to depend on where you start. But if I do the derivative of 2x, I get 2. So the second derivative, okay, is equal to 2, and that's why we see the difference of the differences, which they didn't ask about, are 2. And I just want to point that little extra pattern out to you. See if you can make a prediction, and then they say why or why not. Are there any constant changes? So I'm kind of touching upon the are there constant changes. The constant change is that the differences are constant, not the differences of the outputs. And so you just have to either broaden or expand your lens to find something that's constant here. And that makes sense. When you do the second derivative, now you're taking the derivative of the derivative, and you're showing that those changes are constant. So again, this is to play. This is to have fun. We're just talking about ideas. You're just exploring things, okay? You're not going to get zinged on this. Just complete it, do the best you can. You're going to be just fine. Okay, now C, you're going to do the same thing that I just did for x cubed. See if you can see the pattern that I just spoke about here as it applies to x cubed. All right, and then D is a little different. Let me try to start you off with D and with 6 and 7. Okay, so 5D is asking about a very similar thing to what we did before. Okay, 5D, I'm just going to step you through it. I'm not going to answer it for you. 5D is saying we have x squared, and we know that at 8 we're at a height of 64. And if we had a tangent here, okay, right there, they're saying, assuming you don't know the value of y at 9, so let's just pretend we don't know that it's 981, Like, we'll just put a question mark here. Because we're using x squared as an example, but what if it was like, 3e to the cotangent of theta divided by 6x squared minus natural log of x or something, and our curve was like some crazy old thing. We wouldn't necessarily know what it is. So we're using a simplified case and pretending we don't know what 81 is, and then saying, could we, thinking of this simple case, leverage the tangent line in more complex cases to make predictions about what this value might be if it's too cumbersome to figure out what it would be through basic arithmetic? Because that's what tangent lines help with. When you can make tangent lines of complex functions, you're doing what's called linearization, and you're taking things and making them linear in order to make on-the-fly calculations. If you watch the old series Numbers, one of the episodes talks about this. He's like, well, you just have to make a linear function in your head and do calculations, and it would require somebody who knew how to do that. So that would, and then they narrowed down a pool of who the criminal might be, because the mathematician that was part of the staff was like, they would have had to have done some tactic like this to linearize the complex function. So therefore, of the 15 suspects it could only be this guy because he's the only one that has a math background to do it. So this is a real thing. I've heard that NASA uses linearization for approximates within a certain degree of error. You have to remember, right in here, okay, values within 7.85 to 8.15 or something, these are nearly equal, and depending on how many sig figs you need, they might, for all practical purposes, be equal if you only need precision up to the hundredths or thousandths or something like that. So in some cases, for some functions, the tangent line, what if the curve was not quite x squared, but it was like that, and it swept in here and just skirted along it for super long? Well, that one's it's still curved, but it's really just stretching along it. That might mean that the interval of values where the derivative or tangent line approximated is quite larger. So anyways, you're pretending you don't know that if you plug in 9 it's 81, and they're saying, how could you speculate about it using the derivative of x squared? The derivative of x squared is 2x. How could we use 2x to speculate about it? Well, you can plug in 9 here, okay? Give me 1 second. And if you plug in 9 here, okay, you're going to get 18. And if we take 18 and we add it to 64, you're going to get 12 plus 70, you're going to get 82. So that's all I'm going to tell you. So what do we know about 80? Did I do that right? Let me just make sure I did this right. Hold on. Haha, I did not do that right. We don't want to plug in 9. Sorry, little itty-bitty mistake. We're starting at 8, and we're using, let me just be clear on why we don't want to use 9. We're using, as they said, the tangent at x equals 8 to speculate, because we have a known value. We don't know what the next value is. We know what this value is. So we make a tangent line equation at x equals 8 to speculate about the value at 9. So we actually want to do y prime of 8. And y prime of 8 will equal 2 times 8, which equals 16. We add 16 to 64, and we get 80. So we get y prime of 8 equals 80. How does 80 inform us about the answer to this question? So they're saying, use this, make an estimate of this for the value at y equals x9. I think we did that. And then, is this an over or under estimate in y? So I'm not going to answer this last question. I want you guys to do that on your own. But I kind of stepped you through and started it off here, and sorry about doing that. But yeah, you want to you only know about this. They said pretend you don't know anything about this. So there's 2 reasons we don't want to do that. One is we don't know anything about that, and second, we have the tangent here. We don't have the tangent here, so we're using this tangent line to approximate about that point. So that looks good to go, and now, our next question is saying, let's look at our next question here and make sure that you guys know what to do for 6 and 7. 1 second, please. So I'm not going to answer these. I'm just going to zoom in and make sure that you understand what's being asked, because it's a little hard to see. I'm even going to get bigger than that. I'm going to get 200, because it's real easy to miss. And if you look here, they're saying input variable is year, output variable is company's profit. Notice right there, there's a prime symbol. So this is saying, what is the meaning of the derivative of these two units? So instead of doing things purely abstractly and talking about slopes in every single case, what's the derivative of x cubed? 3x squared. And what is its meaning? It means the slope of x cubed at any point. Then we take x squared. Well, what's the derivative of x squared? 2x. Well, what's the meaning of 2x? It's the slope at any point on x squared. Well, what if one of those functions actually represents something in the real world, like years and profit? Well, then the slope actually has dimensions or units. So what would the rate of change of years to profit, what would the meaning of that be if our input on the derivative was the year 2016 and we got 23 out? What's the meaning of that? Okay, here again, years since 2010, Y, price per stocks, Y prime of 6 equals 14. So don't just say slope here. Slope's not enough. What we're asking now is, since there's actually dimensions or units to X and Y here and units to X and Y here, what we're actually asking you is to explain the meaning of what the slope means in this case from the units given. So 6 and 7, when they say explain the meaning, they are asking you to tell us what the slope means at that point for each problem in terms of the units given. Okay, and don't use math talk. Imagine you're the math person and you're at some board meeting with people that aren't necessarily good at math. And you've done all this math to make some predictions or evaluations or critiques of their business for each of these years for these two different scenarios. You're going to go into the board meeting, you're not going to say, well, the meaning of this is that the derivative at 2016 is equal to 23. The meaning of this one is that the derivative at 6 is equal to 14. Because they're all going to look at you and say, well, what does the derivative mean? And what does it mean in this context? What does it mean in terms of stocks and years? What does it mean in terms of profits and years? So plot out your X and Y. I guess the last hint I'll give you is, maybe remember Leibniz notation, d dt, right? Or d dx, or whatever the independent variable is. So here we have x and y, so this will be dy dx. What's the meaning of dy dx for both of these scenarios? There's obviously two. So x is years, y is profit. So change in profit according to years. All right, that's the last hint I'm going to give you. Try to muscle through 6 and 7 on your own. We're just looking for a sentence here. You don't have tons of math to do on this exploration. You're just giving me a sentence here and a sentence here and thinking about what these mean, filling in a few values on these tables, talking to me about whether this would be an over or underestimate. Go look at the first part video for today. We kind of talked about that. And just think and explore and dance around with these ideas. See if you can find the same equivalent pattern to what I found for x squared for x cubed. And have fun with this worksheet. It's very lightweight. I did the first 4 for you. It's just designed to get you thinking about derivatives in a little bit more robust way. And enjoy. And this is our last video for Flipped Week, and I hope you all are doing very well.